Okay, so it's about time. Everybody, good afternoon. Welcome back to DSP. And today we will continue this lecture number 5. And the topic is a kind of system which is called linear and time variant. And by this, we will also we're going to officially introduce Z transform in more details. And so what is a system? A system in this course refers to something, a block, a building block. A system receives input and produces output. Okay, so that's our simple definition. A system. What is a system? A system is something that receives an input and produces an output. And so with that definition, so we can talk about the property. What do we mean a system is linear? So let's take a review, a recap here. If we write our system using this script H, 草写, script H, and so H receives an input X and produces an output Y. So linearity means that when we linearly combine the input, the output is also linearly combined with the same coefficients alpha and beta. Very simple definition. So, and in particular, when the input doubles, the output also doubles. 2倍, 2倍. So that's linearity. I'm quite confident that you guys are familiar with the concept of linearity, 线性, linearity. And then, time invariant means that, officially means that if we delay the input by m samples, the output is also delayed by m samples. Very simple definition. And these are definitions that we can check mathematically. So given any system, you'll just check property number 1, property number 2 to see if the system belongs to LTI, linear time invariant, LTI. So that's the terminology. Okay. So with this definition, we also brought to you the concept of the importance of impulse response when we discuss an LTI system. And here is the idea. The impulse response, by definition, is the system's response to what? When the input is delta. Okay, when the input is 1 unit of delta, the resulting output is called the impulse response. And very soon we realize that by definition, if H is linear and time invariant, then its output that it produces when receiving any input equals to that input convolved with H, small h, its impulse response. And here note that this is a convolution operation right here. Okay? For any input, okay, if the system is LTI, then for any input, the output is going to be X convolved with H. And what is H? H is the impulse response. Okay? And this is a very truly important concept. Can I ask you not to eat in this classroom? Yeah, everybody, yeah, can you cooperate? Yeah. We mentioned this at the beginning of the semester. Okay, yeah, thank you for cooperation. And there's the other room that you can feel free to do what you like. Yeah, thank you for your cooperation. All right, so this is an important concept, truly important concept. Perhaps the number one most important concept right here in this course, because here we say, because of this, we say an LTI system is characterized by its impulse response. Okay, that means that characterization 被刻画 in Chinese, a linear time invariant system is 受到它的 impulse response 刻画, is characterized. That means that all you need to know about an LTI system is its impulse response. This is all you need to know. Why? Because once we know this, we know how to calculate the output for any given input. Okay? So the system is, even we can emphasize that an LTI system is completely characterized by its impulse response. Let me repeat that. An LTI system is completely 完全的, completely characterized, if you will. Completely 完全被刻画, completely characterized by the impulse response, denoted as H, small h. So it's of central importance in this course. Later, we'll look at a particular family of examples. We'll be using difference equation to define LTI systems, and in that, all you need to know about a difference equation with input on the right, output on the left. All you need to know about a system like that is the impulse response if the system is LTI. Okay, so we'll see a few examples today. So far, so good? Yeah? And causality, the next definition that we introduced last week. Yeah. So we say a system is causal if its impulse response is R0 before time 0. Very simple idea. Time 0, and the word causal or causality, meaning this property. If a system has satisfies this definition, then the system is called causal, and we say causality. Okay? This property is referred to as causality. Causality of the system, and meaning that the impulse response is 0 before time 0, all 0 before time 0. And that makes a lot of sense, because in real world, no system can produce any output before it receives any input, right? Yeah, so that's kind of the philosophy behind this definition. Yeah, so, and that's why in this course we're mostly interested in causal systems. In this course, okay? In the textbook or in signal and systems, sometimes they have a long discussion about any system that could be non-causal. But in this course, I want to emphasize that mostly we're interested in causal systems. Okay? Mostly, that's our interest. And you'll learn to analyze the causal system. You'll also learn to design a causal system. Okay, we promise you. You will learn how to design causal systems. But this is also important to know that if an LTI system is causal, then still, yeah, Y is equal to S convol with H for sure. Yeah, that still holds. Yeah. But note that here we can just modify the upper limit of this summation to the current time. Okay? All you need to do is to sum up from the past, from long ago, to the current time. Okay? Because future does not need to be considered. Future input values do not need to be considered when we need to calculate the current output. Okay? They don't need to be considered. So that's the meaning of this equation, causality. Right? So far, okay? Yeah. So a bit of a recap from last week. So here we are going to, maybe not in this lecture. Here, let me also mention that actually later we will analyze exactly this equation. Right? So, but let me just do a bit of a recap that we mostly, LTI systems is a larger class, okay? But we are particularly interested in this kind. LTI system that can be defined by difference equations, by a difference equation, Chaffen-Function, difference equation. And a kind of example, a famous example actually, is this. When the current output is the sum of the past two samples plus any input that the system receives. This equation defines a system with input on the right, output on the left, and some kind of feedback. Okay, yeah. So the output can be calculated iteratively. 用递回的一直往下算. This output it depends on past output, past two samples of output plus any input that the system receives. And I said this is famous because if you think about this, this system gives you the Fibonacci series, the Fibonacci sequence, Fibonacci 数列, right? Do you see that? Does everybody see that? This sequence, or should I say the impulse response? if we consider impulse response, so this is a system. Y equals to, this is just a system, which is linear and causal and time variant. And so then the impulse response, this impulse response is defined as what will happen when the system receives the delta function as its input. That's the definition of impulse response, right? So you'll see that the impulse response right here would be if x is, if our input is 1 at time 0 and 0 elsewhere, that's a delta function. Okay? So if this is our input, basically the delta function, then we can just take a sample of x and put it to this equation and calculate the output. And then for the next sample, let's take the next input sample, and now yn becomes y is delayed by one sample, yn minus 1, okay? And then calculate the output again, iteratively, repeatedly. Then we can produce one sample at a time, right? We produce one sample at a time. If you're with me so far, we are going to produce one sample at a time. So let's see how that happens. So if x0 is 1, then h0 equals to x0 equals to 1, right? Now, how about h1? h1 now equals to what? Let me just say y, okay, y0. y1 equals to y0 plus y minus 1 plus 0, because now there's no input, okay? If x is delta, right? If x is delta, then, but now, here's what I mean. Repeatedly, we will be using this equation, repeatedly. So now y0 is right here on the right-hand side. So we got 1 plus 0 plus no input is still 1, okay? And so on. So y2, let me give you one more example, one more sample. Let's look at this one. What is y2? y2 is y1 plus y0 plus there's no input, okay? When the input is delta function. When the input is delta. So there's no input, then it becomes 2. And very soon you realize we get the next sample is going to be the sum of the past 2 samples. So it's the Fibonacci sequence we're going to get right here. So y1, 1, 2, 3, 5, 8, and so on is the Fibonacci. It's a Fibonacci sequence. All right. Is that okay? We agree on that? We have a difference equation which is time invariant and linear, and all we need to know is the impulse response. And what is the impulse response? Just by keep using this equation, by repeatedly using the equation, we see that the impulse response is 1, 2, 3, 5, 6. That's a Fibonacci sequence. 费氏数列. So this is just an example, and it's linear and time variant for sure, and it's also causal. The way we use it is a causal way of using this equation. With a system, this equation defines a causal LTI system. But this is just one example. So more generally, we are interested in any such kind of difference equation with arbitrary coefficients. Here the coefficient is 1 and 1 and 1 right here. That's just one example. We are interested in generally such kind of equation with any arbitrary coefficients. 就是那个系数可以是任意的. We're interested in all linear constant coefficient difference equations. So we will take a look in the next lecture. But now, So this is where we're at last week, last Wednesday. But now, before we move on to a general discussion of solving, how to solve the difference equations, before we learn how to solve, how to analyze the system, it's a good time that we may want to introduce this transform by the name Z, Z or Z. Z transform. Z transform. And the reason we are going to introduce this is because it's going to be super useful for analyzing LTI systems. Okay, indeed you need to learn. We do need to learn this as a mathematical technique, a very powerful technique. And so let's take now we begin today's lecture by looking at the definition. Okay, so we look at the definition first. Suppose that we are given a signal denoted by P, okay, P being any sequence, or you can say that suppose that P is a discrete time signal with index n is integers. And then the Z transform is defined as, okay, so when I use the column right here, column is the 冒号, when I use the column right here, that means defined as, okay? PZ is defined as this summation. That's what I mean. PZ now, how is it defined? PZ is defined as this summation of Pn, Z to the minus nth power, okay? Z to the minus, there's a minus sign right here, nth power. And in general, Pn, because here we're talking about a signal, okay? Not necessarily an impulse response or something, just a signal. So in general, this index can be from minus infinity to infinity. Okay? And that's the definition of Z transform. Okay? So far so good? Rather simple definition, but be careful. Even though this definition is careful, it's a valid concern. 这是一个合理的一个怀疑啊. It's a valid concern. Yeah, if you're concerned about conversion, your concern is valid. 这样子的担忧是合理的. Your concern is valid. So therefore, I've been careful right here. I say, yeah, this is a definition for sure, but we can attempt to evaluate this expression. You can try to. We can attempt to. I'm being conservative right here. 有点保守. I'm being conservative right here. We can attempt. You can try, okay? I can suggest that you try. Being very conservative. I can attempt to evaluate the following expression. On the complex plane, by the way, Z is complex number, okay? On the complex plane. And the problem is that the concern is that sometimes this expression does not converge. Okay? In general, it can diverge somewhere and converge somewhere, okay, on the complex plane. So in most generally, if you're given a sequence, this expression does not always converge, okay, for any given Z. So that's a concern. So when we write down this definition, we say this definition makes sense only if it converges somewhere. Okay? So we need to be concerned about the region of convergence. Where exactly does this expression as an infinite sum, does it converge? That's a valid concern. We need to be concerned about that. Okay? But that being said, of course, the expression-wise, this is a definition. There's no doubt about that. Okay, this is an expression that we can attempt to evaluate. Sometimes it diverges, sometimes it converges. Okay, there are different criteria, so we'll be taking a look at that. So is that clear? So far, so good. We have an expression. We can try to evaluate it, but there's no guarantee that it converges everywhere. There's no guarantee. Actually, most generally, this expression converges somewhere and diverges somewhere. Okay? Yeah, so this is a valid concern. Keep in mind. But the next thing it's worth mentioning is that if the expression converges on the unit circle, okay? if this expression converges, and we attempt to evaluate this expression on the unit circle, and if we are fortunate that the expression converges when we substitute z equals to e to the j omega. When we do this substitution and put it inside here, the summation, if the summation converges over there on the entire unit circle. So by unit circle, we mean really e to the j omega, okay? So this plot is going to be showing up a lot. Suppose that we have a circle of radius 1 on the z-plane. Real of z, imaginary part of z, okay? Suppose we draw a circle which are centered at 0, and if this is a circle, imagine we have a circle of a radius 1, 半径等于1, radius 1. That's what we call this circle. This is called the unit circle. Okay? A bit of terminology. This circle is referred to as the unit circle. And this is the way I denoted z. It's a set unit circle. This unit circle is a set of z where z equals to ej omega. Maybe I should say, if you will, omega is real. Omega really is this angle, right? Okay, omega is this angle. So this unit circle is on the complex plane. It's on the complex plane. But if somehow we put z equal to a point on the unit circle and put it in here, how we get it right here? The z to the minus n becomes e to the minus j omega n. Is that clear? And we have seen this before, right? We have seen this before. What is it? It's exactly DTFT, right? So this is so now we realize that wow, there's a relation between Z transform and DTFT. In that DTFT is Z transform evaluated on the unit circle. Okay? Let me repeat that. DTFT, by definition, is Z transform. DTFT of something, of a signal, is the signal Z transform evaluated on the unit circle if the summation converges. Okay? So that's a relation between DTFT and Z transform. So finally, this relation explains why our textbook denotes DTFT as big X and with a parenthesis. And inside parentheses, that's why the textbook puts e to the j omega inside these parentheses. Okay? That explains why. Because now we have a unified notation for both the Z transform and the Fourier transform, same expression. So earlier in this course, we say we will take the Fourier transform and denote the result as x ej omega. Okay? And it's equal to sigma over all n, xn. And in this way, we go from the time domain to the frequency domain. So previously, we emphasized the idea that we are going from time domain to the frequency domain. But then that raised the question, why this notation? Because just going from time domain to frequency domain, why don't we denote the result as simply something as a function of omega, which is true, yeah. This is certainly a function of the frequency, right? But why didn't we denote it as simply big X of omega? In some other textbook, yeah, sure, this is a valid notation. Notation is just notation. Use whatever you want, right? But there's a reason why the textbook suggests that we put ej omega inside here. And the reason is because we want to have a unified notation, okay? Emphasizing that DTFT is Z transform. Yeah, now Z transform, DTFT, if you just use script Z to refer to Z transform, and big X of Z equals to summation over all n, we attempt to evaluate this summation. You can do that, not E, no, Z minus n, okay? But very soon you realize now this notation and that notation, the two notations are unified. It's not tricky, okay? So it's a choice. Yeah. That's why the textbook chooses to have this kind of notation for DTFT instead of that, okay? Instead of that. Not saying that this is wrong. This is all right, yeah. But in the textbook, let's follow the suggestion. Let's follow the recommendation that we'll put this as our notation for DTFT. Okay? Is that clear? DTFT is what? DTFT is Z transform evaluated on the unit circle. Okay? Calculated, when you compute Z transform on this circle, that gives you DTFT. Okay, so that's just a bit of a remark about the notation. It's a remark. It's just a remark. It's not hard. It's just a remark. And now, the next thing we need to talk about is the convolution theorem. We already know that in DTFT there's a convolution theorem, which tells us that when we convolve two signals in time, then the spectrum is going to be multiplied. Convolution in time domain, multiplication in the frequency domain. So that's what we previously introduced. That's called the convolution theorem. But turns out that in Z transform, we also have very similar property. If the two signals are convolved in the time domain, then when we go to the Z domain, the Z transform multiplies. Okay? The two Z transform multiply, and the result is on the left. So that's also called the convolution theorem. And a bit of also terminology. So a lot of time, usually we try to, in our notation so far, in the context, most of the time the context is X being the input, Y being the output, and H being the impulse response. That's our context, right? In LTI system, if X is an input, the H might be an impulse response of the LTI system, and X will be any input that the system receives. Then when we go to Z domain, there's a nice relation. The output Z transform equals to big H, big X multiplied. So we often call big H the system function. And when we evaluate the system function on the unit circle, then that's called the frequency response of the system if it exists. Okay, still, if the summation converges. When we say exists, we mean if the summation converges. If the summation converges, that's what we mean exists. So the meaning of this system function is that when we evaluate everything on the unit circle and suppose that everything converges, both big X, big H, and big Y. Okay? If big X and big H converges on the unit circle, then here, this we take the absolute value. Take the modulus. Take the absolute value 模数. take the. I often say absolute value. But in complex theory, it should be modulus. Anyway, take the absolute value that gives us the gain which a signal will receive at frequency omega. Okay? And we mentioned previously that this term is called the magnitude response, whereas the argument, or the angle of this And note that in general, this is going to be a complex number. Okay, so you can talk about the angle. Yeah, so the angle here means arctangent of imaginary part of H divided by real part of H. Okay? That's called the phase response. Right? Yeah. So also, yeah, we have the absolute value. The magnitude response is, you know that what that means, real part square plus imaginary part square. Sum of square, take the square root. That gives you the absolute value. Okay, that's called the magnitude response and phase response. Okay, and now when we evaluate these over big H, H characterizes the system. Okay, so so the meaning is that now this magnitude response means it gives us the gain a signal will receive as a function of frequency omega. Whereas the angle right here means a phase shift that the system introduces also as a function of omega. Okay? Phase response, magnitude response. But here, just on this, the overall theme is convolution theorem. Convolution theorem is still valid right there. Convolution in the time domain, multiplication after these transform. Yeah? Okay? So I probably leave the kind of, you can check it, okay? You can check it by yourself. That is true. But I want to mention perhaps, yeah, actually, let's check. Let's do a quick check together. H of z, okay? H of z, what is H of z? H of z is summation is H0 plus H1 z minus 1 plus H2 z minus 2 and so on, as well as H minus 1 z, H minus 2 z squared, and so on. Okay? But if H of n is all 0 before time 0, or in other words, if the system is causal. So let's consider the special case. If the system is causal, then we can erase that. Okay? So H is going to start from here. The first term right here, the leading term is a constant term. Okay? Yeah. And what is X? X is generally any signal. Okay? So the Z transform right here would be, now we need to sum up all n. Okay? Yeah. Oh yeah, actually I can put in here, and still, this is still going to be true. So now, to do a quick check of the convolution theorem, we would multiply big H with big X. So let's multiply the two of them in the Z domain. Okay? So in the Z domain, when we multiply H with X, so that means summation n H n Z minus n, summation n x n Z minus n. Yeah? the result so the result so the question is whether or not the result is summation n yn z minus n, where y is x is a convolution. That's what we need to check. So I guess basically I'll leave this as an exercise, okay? I'll leave this as an exercise. Perhaps easier to go backward, okay? Because we have done the backward, but it's also possible to do this forward direction. The backward direction is just very similar to what we have introduced previously. When we check the convolution theorem, we start from the time domain. Okay, let's say we start from the time domain saying that now y is x convolved with h, and we can see we have verified that the dTFT of y equals to the dTFT of x times the dTFT of h. We've done that before. So that path is easier. But now, the forward path is also doable. 也可以做, it's also doable this way, going this direction. And the key point is to有点卡住。I don't want to get stuck forever right here. But the key point is that the result is still in this form. Okay? Y is unknown. Okay? If we go this direction, Y now, let's say now if the result, we don't know for sure whether or not it's Y. Okay? If we call the result Y question mark, okay? Y question mark, it's not necessarily Y, okay? We call the result Y question mark, but the key idea really is that when we multiply two expressions like that, the form, the result will be in this form. The result still will be in this form, okay? Because for every for example, let's consider the constant term, okay, the constant term. The constant term is going to be h0, x0, plus what? Plus h1, x minus 1, plus h2, x minus 2, and so on. That's a constant term. And now you can consider what's the z minus 1 term. Okay, that's what I mean. The z minus 1 term, what can we put inside here? What can we put inside here? We need to match z minus 1 with x. So it seems to me that it's going to be h1 x0. Plus what? No. It could be h0 x1 h1 x0 plus h2 x minus 1 and so on. Okay? So just by comparing coefficients, what is this? This is going to be y question mark 0 by construction. And this term is y question mark evaluated at time 1 and so on. Okay? I better stop right here. Yeah. So it's doable. It's doable just by comparing the coefficient to convince ourselves that every coefficient y question 0 is in exactly y0, where y is defined as x convolved with h in the time domain. Okay? So you're able to just verify that every term, in every term the coefficients are the same. Therefore, completing our check of convolution theorem for the transform. Okay? I think I'm not doing a very good job today, but it's doable. Okay? Much easier to go backward. Much easier to go backward and say that if y is indeed x convolved with h, then the z transform for y is indeed x times h, big X, big H. Okay? Much easier that way. Probably, yeah. Maybe you can forget about my attempt. Yeah. I see most of you are lost. Sorry for losing you. I'm kind of getting sidetracked. Yeah, I admit I'm getting sidetracked on this derivation. And also losing my monitor. What's the password here? Oh, 你刚刚告诉过, yeah, password. I do remember the password. Right, yeah. Anyway, so I think this is actually not hard. You will learn, you'll see what's going on right here. The important thing is convolution theorem, okay? Convolution time, multiplication in the Z domain, okay? Let's just move on, okay, from here. Let's move on from here. Okay, so here is an example. Here, example, now we have a system defined by an equation, and with our input on the right, output on the left. Okay? And from here, we can do a few things. We can, and I call this system a numerical differentiator, a numerical differentiator. Because it resembles differentiation. 微分啊, one sample and minus the past sample and divided by how much time has been passed, one sample. If the time passes by one sample, what is time? The time is the sampling period, okay? So so taking the limit when delta t approaches 0, it gives you the first derivative. Okay? In that regard, we call it a numerical differentiator, 数值的微分器啊。Numerical differentiation. So this is an example. And we can calculate we can try to answer a few questions. First of all, is the system causal? Is the system causal? Okay? Whether or not the system is causal. Yes, it's causal. Okay? Why? And because probably we can just when we check whether or not the system is causal, we need to calculate the impulse response. Okay, so this is a good example where we can check some definitions. So now we can talk about h of delta, right? When the input is delta function, then the impulse response, if you give a plot, you can plot for time 0, the impulse response should be 1 over t, right? That's for at time 0. And for time 1, the impulse response should be just minus 1 over t. That's the second sample for the impulse response, small h. And so on. But now, the next sample is 0. And thereafter, all 0. Also, at negative time, there's no impulse response. Okay, so the system is causal in what sense? The system is causal in that its impulse response is all 0 before time 0. Okay, so therefore, because h of n is all 0 for before time 0, therefore, yeah, this system h is causal. Okay, so that's a rather easy thing to check. So far, so good. Yeah, the impulse response for using this equation is going to be just keep using this definition iteratively. Get a new sample of x, compute y, get the next sample of x, compute y, and so on. You'll be able to see that after first two samples, when we go to the third sample, if the input is delta, the output is going to be all 0 after the third sample at time, starting from time 2 and beyond. It's all going to be 0. The impulse response is going to vanish after this time. Okay? It should be pretty clear. This is rather easy. Okay, I guarantee you this is rather easy. You can figure that out. But I want to mention that for this kind of systems, so very soon you realize that if we don't see any y on the right-hand side, that means there's no feedback. Okay? If you don't see any y on the right-hand side, there's no feedback. And you recognize, you will learn to recognize that since there's no y on the right-hand side of the equation, the impulse response is going to vanish after a while. 过一会儿就等于0了. It's going to vanish after a while. So here it's vanishing. After a while, after n greater than or equal to 2. Vanishing, 意思是等于0. That means equal to 0. It's a good word to know. Vanishing, 消失, vanishing. The impulse response vanishes after time beyond time 2 or later. Okay? So there's some terminology for this kind of system. Okay? There's a terminology. We call that this system is FIR. Okay? We call that this system has a finite impulse response. It vanishes after a while, finite impulse response, or FIR, and we will come back to that, a bit of a terminology. Okay? And there's another class system where the impulse response lasts forever, theoretically. exponential decay but lasting forever. So for those kind of systems, we will call them infinite impulse response. Okay? Finite impulse response, infinite impulse response. Okay? So there's another kind of system called IIR, where the first I stands for infinite impulse response. Okay? IIR stands for impulse response. Two different kinds of systems. But here, for sure, since Y does not occur on the right-hand side of the equation, the response vanishes after two samples. Okay? Beyond the two samples, there will be no further. The response is no further. Okay? So we call that the impulse response is finite. Okay? So let's take a break of 10 minutes. When we come back, we calculate. We do a sketch of the. We do a sketch. We answer. We will sketch the magnitude response and phase response when we come back. Okay. 其实是对，跟上次一样。不过有一点小观念，刚刚如果是 Okay, so let's go back. Yeah, so we have some. Oh, by the way, next week is going to be the Wednesday. We're still going to meet on Wednesday for next week, but next Thursday is there's no class. Yeah, but the week after that we have the first midterm. Oh, let me friendly remind you, friendly. Our first midterm is going to be the week after that, okay? So please be prepared. And that's going to be, I think, April the 8th, okay, if I remember correctly. The week after that. Our first midterm is scheduled on April the 8th. That's a Wednesday, the Wednesday in class, okay? And the coverage will be anything till the end of today, okay? So we'll still have something to cover, but wherever we stop, that will be the end of the coverage for the midterm. So that being said, is that clear? So next week we will meet in class, but the material we cover next week will not show up in the midterm, in the first midterm. Is that clear? So anything covered today will show up. It's likely to show up on the midterm, but whatever we cover next week will not show on the first midterm. Okay? 就是考到这礼拜为止啊。Is that clear? Yeah. Is that clear? 考到这礼拜为止啊。Next week we still meet, but the material right there will not be in the first midterm. It will be in the second midterm, but it will not be in the first midterm. Is that clear? Okay, so before we resume, let me try to give a better explanation of where I was struggling right there. Okay, I was struggling there trying to show you that when we multiply two Z transforms in the Z domain, that gives us a function of Z, but that function of Z corresponds to the Z transform of convolution. That's where I struggle. Okay, I struggle to show you that if small y is x convolved with h in the time domain, then big Y is h times x in the Z domain. I struggled to show you. I was struggling. 是在挣扎啊。So it's probably easier to look at a particular example, special case. Okay, special case. It's easier to look at a special case when to see what I was trying to say. Okay, so let me just confine our interest in this special case. Let's assume for now, okay, h is all 0 before time 0, and so is x. Let's focus on this special case first, okay? And so is x. X is also all 0 before time 0, okay? So then by definition, Hz, the Z transform becomes a power series. So now with the leading term being the constant, okay? Because of this property, now H of Z is a power series. Is a power series of Z to the minus 1. Can we agree on the power series? Now this terminology is like a generalization from polynomials. 多项式的推广版, okay? When we have infinitely many terms, we call it a power series, right? So now, if we confine our interest in this special case, then the Z transform by definition becomes a power series of Z inverse. And just allow me to further simplify our notation. H0 using subscript, okay? H0 is H0, H1 is H1. Yeah, but just to save space. 省点空间啊. So can we agree that I use some more compact notation, 比较简洁一点啊. 0, 1, 2 being the time index, okay? And similarly, x now is also a power series with infinite sum right here. Okay? Both of them becomes power series. Like polynomials. Think of polynomial. It's like 就像多项式一样. Yeah. Both of them are power series. But now, when we now multiply the two of them, try to think of it. What happens when we multiply two power series? The result is still a power series, right? It's just like when you multiply two polynomials, what's the result? The result is a polynomial, We are okay with that, right? When we multiply two polynomials, 两个多项式相乘. When we multiply two polynomials, the result is also a polynomial. We can agree on that, right? It's very intuitive. Now similarly, when we multiply two power series, the result is what? The result is still a power series in the form of a constant leading term plus something is coefficient z to the minus 1 plus something z to the minus 2 to the minus second power and so on and so forth. The result is still in the format of a power series. Okay? So now we just need to fill the blank. Can anybody tell me what's here? What's the leading term? The leading term, the constant term, certainly is h0, x0. When we multiply the two of them. Yeah? That's what I'm trying to where I want to go. So the first term certainly is x0, h0. Yeah. That's the first term. How about this term right here? Where do we put in here? Where do we put in here? So note that here we need to collect, okay? We need to collect a sum of products, okay? We need to collect, when we multiply, think of them as polynomials, right? Think of that polynomial, the coefficient to the first power, we need to figure this out, we need to collect terms. And there are two terms. There are two terms. The first term should be h0, x1. The second term should be h1, x0. Just think of pretend that they are polynomials. Okay? Does that make sense? If we pretend that these are polynomials, it's just like 多项式嘛. We pretend that these are polynomials, it's very simple, right? We all need to do, we all know how to multiply two polynomials. Does anybody not know how to multiply two polynomials? 多项式相乘会算吧? Right? Right? Yeah. So they're just like polynomials. Now, what we put in here is certainly h1 x0 plus h0 x1. So that's where we put in the kind of first power term. And then we are ready to move on to talk about the second power term. Can anybody tell me where we put in here? Where do we put in here? Pretending that they are polynomials. Pretending they're polynomial, right? What do we put in here? 你假装它是多项式啊. That's where I struggled to show on the right. So now, is it clearer? Is it getting clearer, right? What do we put in here? We put in, let me sit down. We put in this times that, plus that, and that, right? So h2 x0 plus h1 x1 plus h2 x0. And what is this? Now you see that? Now, this is exactly a convolution, right? This is in the form of a convolution already. We flip x and multiply it with h, right? So this is convolution, this is convolution, this is convolution, but it has only one term, okay? So now, by definition now, so therefore, if yz is the product of h and x in the z domain, then yz corresponds to yz is a power series. Yz is also power series, and by definition, we know yz is by definition defined as summation n yn z minus n. Okay? So on one side of the equation, we have yz by definition. Big Y is the z transform of small y. But we also for this path, we also realize that yz being the product of h and x y is equal to blah, 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 this long, very busy expression, right? Busy expression. But when we are ready to do coefficient comparison, 比较系数法. Now we're ready to say, on one hand, this is yz by definition that, a power series. But on the other hand, yz equal to this very busy expression. They are equal everywhere, right? They're equal everywhere. They're equal everywhere, and the only possibility for them to be equal is that every term is equal, respectively. 各自都相等. This term, y0 got to be equal to z here, y1 equal to that, y2 equal to that. Therefore, y is x convolved with h in the time domain. Long story short, okay, for this special case. Okay, for the special case when we assume both h and x are 0 before time 0. You see the last very beautiful step? Yeah. This is definition, this is derivation. Derivation right here, definition right here. They're all equal, so the only possibility for them to be all equal, for the two expressions to be equal, is that every term is equal. Okay? The only possibility for two power series or two polynomials, if you will. 两个多项是要相等，一定是逐次要相等嘛，才会是恒等式。Okay? So the only possibility for two power series to be equal everywhere is that every individual term is equal respectively. 各自都相等。So by doing that, we call this coefficient comparison, 比较系数法. So we compare the coefficient right here and right there, you realize, oh wow, indeed. Therefore, y is equal to x convolved with h evaluated at time n, okay, for every n. Okay, so that's kind of so that's what I want to tell. I wanted to share with you this other kind of alternative perspectives, 不同的视角, 不同的 viewpoint. And now you can probably see why I struggle. Why I struggle because without first focusing on this special case, 如果我们不先 focus on 这个特例化, without focusing on the special case first, it's harder to tell the story, basically. The idea will be similar. You can now generalize. You can now lose this constraint. We loosen this constraint, 把它放松, and see how can you generalize it to a more, how can we loosen that constraint? But it's easier to first look at this special case. Okay? The final step involves comparison of coefficients. So, yeah, it's good to get stuck once in a while. I don't, I feel okay to get stuck from time to time, yeah. But anyway, let's try to get this alive again. So we can wake this up. We will wake this up. We will wake this up. Okay, so let's get back to this system we are called, will it keep showing up? Hopefully not. Okay. Where's my pointer? Losing my pointer somewhere. 我那个棒棒今天 So we're looking at this equation. And very soon, with this definition, we realize that the impulse response has only two non-zero samples, one pointing up, the other pointing down, okay, with positive polarity and negative polarity. Yeah, so that's the impulse response. You can very easily verify this is true. And now, because the impulse response is all 0 before 0, the system satisfies causality. Okay? The impulse response is causal, and so the answer is yes, the system is causal. And we have drawn a sketch of its impulse response. Now, does the frequency response exist? Yes or no? Does the frequency response exist? Does the frequency response exist? Okay. Now we can attempt to evaluate the Z transform on the unit circle. Okay, let's attempt to evaluate the Z transform on the unit circle. Okay. We attempt. Okay. By definition, DTFT equals to sum over all n, not x, I'm sorry, h. H, that's the frequency response. By definition, is an attempt to evaluate this summation, e to the minus j omega n. Does this summation exist? Yes or no? Yes, raise your hand. Yes. I don't know, raise your hand. Some people don't know. Okay. Yes, it exists. Because it has only two terms. It's not even an infinite summation. Okay? Now, it has only two terms. So, of course, yes. The answer is yes, the summation exists. Because the summation is just h0 plus h1 e to the minus j omega. Okay? And what is h0? h0 is 1 over t. h1 is 1 over t, minus 1 over t, e to the minus j omega. So yeah, of course, the summation exists. It converges because it's not even an infinite sum. That clear? So that's what we need to check when we talk about existence of DTFT. It's a valid concern. Not for this case, but generally it can be a valid concern, okay? We attempt to evaluate this summation. And in this special case, there's no problem because there are only two terms, okay? Of course, it always converges. So it always converges for any omega, okay? For any omega, this expression can be evaluated, so no problem. Okay? So no problem. As long as the system is FIR, there's no problem. No. Okay, so good. Yeah, does the frequency response exist? Yes, it does. So now we are ready to try to sketch the magnitude response and the phase response. Let's do that. Okay. So to do, which one do we do first? Now we have an explicit expression for H, right? So all we need to calculate to do for magnitude response. How do we calculate magnitude response? Maybe a bit of organization. Let's put 1 over t right here, and we have 1 minus e to the minus j omega, which equals to 1 over t. Now, the inside can be further separated into the real part and imaginary part because we are going to use it. Okay, so what is the real part? The real part is 1 minus cosine omega, right? Plus j, the imaginary part is j, actually minus j minus sine omega. That's a system function, or that's a frequency response, okay? That's a frequency response H evaluated on the unit circle. So far so good? So how about now magnitude response? For magnitude response, we just need to calculate sum of square and square root, right? So we will do that. So therefore, the magnitude response is going to be just very simple, 1 over t to the outside, square root. That's what we're going to do, okay? 1 minus cosine omega plus square plus minus sine omega square. So what else? Still 1 over t, okay? Square root, let's expand this. 1 minus 2 cosine omega plus cosine square omega for the real part square. And the imaginary part square obviously is sine square omega, okay? And very soon, cosine square, sine square, right? So cosine square, sine, that's pretty easy. This is 1. So therefore, we have 1 over t, 2 minus 2 cosine omega. So you can stop here or go further, okay? For those of you that are familiar with trigonometry, 三角恒等式, you can go one step further perhaps. We can probably go one step further, but this is good enough. Everything here is correct, right? This is correct, but we might want to go one step further, okay? Can anybody suggest to me what further step might we take? Could we take a step further from here? There's a trigonometric identity, 一个三角恒等式, right? There's an identity of like what? What is that? What is 2 minus 2 cosine? I think it's 4 sine square. Omega half angle, right? Yeah, so that's like one further step. So now, just as a final result, we have 1 over t, and here we might have actually 2 sine omega divided by 2, taking the absolute value. So now everything's real, okay? So that's the magnitude response we're talking about. And yeah, getting in the middle. Okay, so that's, we now are ready. We are now ready to make a sketch of the magnitude response. Yeah, make a sketch. Now we make a sketch of that. Now we make a sketch of that, okay? So what's that? Magnitude response. Big H, Ej omega. Absolute value, that's a magnitude response as a function of frequency. 2 sine. So remember that our impulse response is real in the time domain. Therefore what? Therefore the frequency, the first transform has a symmetry. Do we remember that? Okay. Okay, so we plot the dTft from minus pi to pi, right? And with absolute value 2 sine over 2 omega, I think we have this. On top we have, it's like that. And symmetrically that. So that's kind of my way of plotting and making a sketch of the magnitude response. Okay? Where here, yeah. Just doing a plot, okay? Just doing that plot equals to 2 sine omega divided by 2. Okay? Make a plot. Is making sense? No, here I already copied everything right here. Okay, we have an explicit expression for the magnitude response, and here's just a plot. Okay, you can do it by hand, you can do it in MATLAB, or in any method, using any plotting method. So that's the magnitude response. Okay. And how about now the phase response? How about now the phase response? Now the phase response, okay? Now the phase response, one way is to calculate, to consider arctangent imaginary part divided by real part, right? Now, so let's take a look. The imaginary part divided by real part, okay? Now, minus imaginary part sine is it omega, 1 minus cosine omega. So that's an expression. That's an expression. Okay? Now. So to go from there, it could be a bit tricky, but I know this minus sign right here, we can probably move the minus sign to the outside, okay? Minus sign. But what is sine omega? Sine omega, there's a formula. Sine omega is 2 sine omega divided by 2 cosine omega divided by 2, right? That's sine omega. And then on top of that, at the bottom, what is 1 minus cosine omega? We have already shown that 1 minus cosine omega is 2 sine square omega divided by 2. Okay? Right? So that's the trick. You can work out this way. Square. We have a cancellation of sine term. 2 cancel by 2. So hopefully this is not moving too quickly. We have a minus sign in the beginning. Arctangent. Now, this is what? Cosine divided by sine. Okay? Cosine divided by sine, if you will, is the cotangent of omega divided by 2. Okay? Right? That's right. Cosine divided by sine is the cotangent. Okay? And so on. Okay. Yeah. So we're almost there. But then, what is cotangent? Cotangent and tangent has a relation, right? So we have the minus sign still right here, arctangent. But now, cotangent of something is tangent of pi over 2 minus that thing. Right? So tangent and arctangent is inverted. Now the final result should be minus 2 pi Well, I'm about to write down an answer, but I don't think this is correct. Minus plus minus sine cosine divided by sine cotangent so I'm really yes, so you can go through this might not be exactly correct. Okay? I think I'm missing a minus sign somewhere. I remember this part shouldn't be plus. But I struggle again to figure out maybe this expression has been wrong. maybe this expression has been wrong. Yeah, this expression wrong here. Now I realize, 这边错，来，谢谢啊。In English. Right. Extract something. Go ahead. I know. Actually, I know where you're heading to. Yeah. Yeah. What's up? Yeah. What do we do? Uh-huh. Yes. And then let's take a look. Yeah, exactly. Yeah. Yeah. So what I remember is correct. Yeah. Thank you. Okay. So anyway, so let me complete my correction. Okay, right here. I made a mistake, a small mistake right here. Okay. Yeah. So here there's a minus sign, the minus sign, but there's also a minus sign. Okay. So here really there's is plus sign, okay, which does not affect the result right here, but it affects the result right here. Okay. A plus sign. So there's no need to put this plus sign, and the plus. So it's really 2 pi minus pi divided by 2 minus omega divided by 2. So which agrees with, where are you? 刚不是做这个吗？Anyway, 等他回来 let's wait for a moment. Yeah. 我其实是故意的啊。But I knew this. I knew this from long ago. Okay, but it's good that you made this a suggestion. This is a much more convenient, much more efficient, better way to show the derivation. Okay, a better way to show derivation. It's all about symmetry. All about symmetry. Okay. Any other comment? Is that clear? But I just want to use this very simple example to show that given any equation like that, we can verify the system being causal, being the frequency response exists, and then once we realize it exists, we can calculate magnitude response and phase response in principle using the definition. Okay. In principle, even though it's a longer derivation, in principle you can use the definition of absolute value being the square root of something. Follow everything here. In principle, you can reach the same result as being concisely shown using this alternative way of derivation. Okay, for both the magnitude as well as the phase. A longer derivation, but yet they should agree. And thank you for the suggestion. I just said, 其实我知道. I knew it, but I just want to emphasize that you can do this using the very definition. Okay? Yeah. So very good. Any questions? Any suggestions so far? 有没有想进步了解的？We need to fix this. 电机系统认证系统。Let's just turn off the. WiFi 关掉就可以啊。Let me turn off the Wi-Fi. Okay, so that's all I want to show. Do I have one more page? Okay, some further comment. The next lecture will be about difference equations and the Chinese displacement function, and we will learn how to solve them using Z transform. We're running out of time, so let me say that the midterm will cover to the end of lecture 5. Okay, but we have a bit of more time. We can jump into take a preview of lecture number 6, which we will continue next week. Okay, but this will be the end of the first midterm coverage. And please do not find me on Instagram. There's somebody whose ID is linear time invariant on both Thread and Instagram, and please do not find it. Okay, yeah. How much I love this term, this terminology. I name myself linear time invariant. Do not find me because last year, around August, I stopped using Thread. Yeah. Anybody want to guess why? Before that, I was using it. Okay, I admit. Okay, frankly, I was using it until July 20 something last year. There was a vote. Right? there was a vote, and so after the result was announced, I was surprised. So I realized I spent too much time on Thread. One of my posts actually reached almost 1,000 likes. 有一个发文将近1000个赞. I was wasting too much time on Thread. And I realized that most people have different opinions. Okay? So the danger of using Thread is that they tend to lock into your comfort zone. Okay? You'll be constantly reinforced by people that has the same opinion as yours, which is dangerous. Okay? I think I'm very confident to say that Thread is dangerous in that regard. It locks you into a sort of a bubble in which everybody agrees with you always and forever. That's a bad thing. So I stopped using it. The account is still there. You can still find me, but I will not respond, unfortunately. You want to find me on social media, I still use Facebook right now. So that's the end of lecture number 5. And let's take a break of 2 minutes, and then we'll spend about 10 minutes for lecture number 6. 好，我们休息2分钟，好。Okay, take a break of 2 minutes. Really, thank you for the suggestion. I love it. I love it. 好，那走一半。好，那边也烧好了。Okay, so are we ready to learn a few more things, talk about a few more things before we end today's lectures? So this next lecture, number 6, is all about difference equations. And I want to just share with you that we will limit our interest to using these equations causally, using them causally. The reason will probably not be so clear, but we'll clarify what do we mean to use a difference equation causally. So here is the general formulation. Okay, now we have an equation, one line of code, if you will. This looks like one line of code. Can we agree? 一行程式啊. Why you can calculate the expression on the right and store it for the next sample. Okay, so it's one line of code. And inside we have two summations, each being a linear combination. For x, we have a linear combination of the past n samples of the input. That's this term. And we also have a linear combination of past m samples of the output that the system previously produced. So we are looking back by up to m samples to the past, m samples ago, and we're looking up to n sample in the past. And we form two linear combination, and the result is stored as your next sample of output. So that's the equation that we're going to study heavily. A few terminology right here. So when the coefficients right here, when the linear combination coefficients are constants, and they're also assumed to be real valued, and we call this formulation a linear constant coefficient difference equation. Fancy term LCCDE. Okay. Linear constant coefficient, 常系数的, constant coefficient difference equation. They are difference equations. And now, sort of jumping ahead, if we define, because this is a system, so it has a system function defined as a ratio of output divided by input in the Z domain. Okay, so that's a definition. Output divided by input in the Z domain is defined as the system function, which is the Z transform of impulse response. Okay, the impulse response Z transform will equal to y divided by x in the Z domain, and then this is something that we need to understand. Okay? To jump from here to here, we're missing one step. Okay, we're missing one step. That one step is a property of Z transform. You need to understand that when we shift the signal by n samples to the right, then what happens in the Z domain? After Z transform, the result is denoted by big X. But what's happening here? Here it's rather easy to verify. It's very easy to check that when we shift the signal in the time domain, then go through Z transform, the result is going to be the original Z transform multiplied with Z to the minus M. Okay? This is a shift property, a well-known property which is easy to check. Pretty easy to check. If we shift a signal to the right by m samples, the result in the Z transform is going to be a multiplication of this term. Okay? This is a delay term, if you will. Okay? This is what m samples of a delay correspond to. Okay? It corresponds to multiplication with Z to the minus m. Okay? Shift theorem. Rather easy. So I really will leave this as an exercise. It's pretty easy to check. Okay? Pretty easy to check. So therefore, now when we look back in this expression, we have a linear combination. But inside every term is a shift to the past, right? Shift to the right. Every term right here is a shift to the right. Therefore, now let's consider the Z transform. Okay? Now let's consider Z transform with that definition. Then Z transform YZ equals to, because Z transform is linear, so summation is still there. K is going to be 1 from 1 to big M. Now minus AK, those are just the coefficients. But how about the Z transform of, here we're going to put in Z transform of Y shifted to the right by K samples. So that's what we're going to do. And similarly, plus K from 0 to big N, bk, which is constant. And we're going to evaluate z transform of x shifted to the right. Okay? That's what we will get when we take z transform. When we take both sides of the equation through the z transform. On the left, we have big Y. On the right, every individual term is going to go through z transform. And then, what's the z transform of Y shifted to the right? This, respectively, every term equals to z to the minus k y. And similarly, what's the z transform of x shifted to the right by k sample? That equals to z to the minus k power big X. Okay? So now if we just organize our terms a little, so it seems that in every term we have yz, so yz can be put to the outside, right? In every term we have xz, so xz can be pulled to the outside, right? So now next, what we have is yz to the outside minus, let me do the summation, y to 1 to m minus ak, z to the minus k is still here, so let's not forget that. And similarly, the next term, xz to the outside, in here we have summation k, let's be clear, from 0 to big N, bk, which is a constant, z to the minus k is still there. Yeah. So therefore, further, let's move everything that has a y to the left-hand side. Okay? When we move everything that has y to the left-hand side and leave this x term right to the right-hand side, we have yz now 1 plus a1z inverse plus a2z to the minus square plus the highest order term is a big M z to the minus n equals xz b0 plus b1z inverse plus the highest term, if I remember correctly, big N z minus n. We have this after some further simplification. Just moving everything that depends on y to the left, leaving everything that depends on x to the right. Okay, we have a relation of like that. Therefore, this is true. Okay, at least just in terms of the expression, this expression is correct. Now, okay, using the shift theorem. Okay, so next week when we come back, we will just use this convention. We call this, now the bottom and the top, denominator and numerator, both of them are become polynomial z inverse. Polynomial right here, polynomial right there. So therefore we have this notation, okay? We will keep using this notation for the rest of this semester, okay? So be certain that we are familiar with the notation here. Now we denote this expression as b of z divided by a of z, okay? B of z divided by a of z. So from there, we'll learn how to analyze, how to compute. Now for in general, how do we, if we're given this difference equation, we will be able, in principle, to compute its impulse response in closed form. I'll tell you closed form solution. So we'll be using this as an example. Okay, we'll get back to this example of Fibonacci series. We will have a general expression of its impulse response. Okay, A simple difference can be computed by factorization and by what we call the partial fractional decomposition and so on and so forth. And you'll be able to show that, wow, so this is an expression for Fibonacci series, right? 1, 1, 2, 3, 5, 8, 13, and so on. The general expression turns out looks like that. Okay? Yeah. So, but we're running out of time, so we will come back next week, and midterm number 1 will cover from the beginning of the semester to lecture number 5. Okay? Everything until lecture number 5. So with that, thank you for being here. Thank you for showing up. Sorry for the struggling, but hopefully we make a few concepts clearer. And we'll see each other tomorrow for the discussion sessions. Class dismissed. Thank you.